Once you have done the electron configuration for a while, you probably realize that it's getting redundant. It's just repeat the same process, but it's just longer and longer, right? So, and we have the way to make it shorter right here. So if you look at right here, neon, sodium, magnesium, all this right here, sodium, magnesium, all the way to chlorine, the first three orbital, 1s2, 2s2, 2p6, they are exactly like the electron configuration of neon. See that? Look just like neon. So in this case, we can write it as neon in a bracket, right? This stands for 1s2, 2s2, 2p6. It stands for the electron configuration of the neon. And then we put only the valence shell outside 3s1, and that's it, right? Sodium have the valence electron 3s1, right? Magnesium have the valence electron 3s2. Aluminum valence electron 3s2, 3p1, group 3 valence electron, right? So the neon in the bracket right here, which is the electron configuration of neon, is called a core electrons or noble gas core. So shorten the way you write electron configuration. Basically, it helps you a lot. Okay, and valence electron still there. The conventionally we do the noble gas core to just leave the valence electron, because the valence electron is really important. You will see it later. All right. So magnesium, we can rewrite it as neon, and then 3s2, leave the valence electron. Okay. Can you pause the video right here? Rewrite the electron configuration of aluminum all the way down to chlorine using the neon gas core. Okay. And then check this with me. Aluminum, got that? So 3s2, 3p1 show leave the valence electron. Silicon right here, 3s2, 3p2, neon inside. That's phosphorus, that's sulfur, and that's chlorine. Okay, so it shouldn't be that hard in here. This is simple there. All right, now we have to pick the right noble gas core. All right, so if you look at this, right here, this is the neon core, right? This is the neon core, but if you go to a larger atom, the electron configuration is getting longer, and longer. And this right here, this does not represent the valence electron of potassium anymore. But the valence electron of potassium just 4s1 right there. The valence electron of calcium just 4s2, right? So we try to shorten the electron configuration even further, right? So using just the neon, I mean, it starts getting redundant now, getting longer. But here's what you can see. Well, for potassium, calcium, and iron, this looks just like the electron configuration of argon. See that? And hold on, we leave the valence electron outside right here. See that? That's a valence electron outside. All right? So that's the argon core. So instead of using neon for potassium, calcium, and iron, we use the argon core, or argon core, right? And you get a valence electron outside right here. All right. So the question is, which noble gas core are you going to use then? Right? When are you going to use neon? When are you going to use argon? When are you going to use krypton? Right? So we use all noble gas in here, but which noble gas are you going to use? So there's a rule right here. So let's see. It's not going. Hold on, over here. For neon, right? For neon, the elements below neon, the whole row below neon, from sodium to argon, use neon core. All right. For once you get to argon, it's getting long now. So we restart right here. There's a new core. Anything below argon, we use argon core. All right. Once you get to the krypton still use argon core, but anything below krypton, that's your new reference now, new core. Anything below krypton, use krypton core, right? And it just goes from just like that, right? Xenon, anything below xenon, use xenon core. Okay, shorten. So every time you go down to argon, krypton, xenon, you shorten the electron configuration, all right? Okay, all right, write full and condensed electron configuration. Do on your own and then compare with me, okay? For fluorine, so 9 electrons, so we go 1s2, 2s2, that's 4, 5 more, 2p5. Right? Now, fluoride. There's a fluorine with a negative charge. We call fluoride. Fluoride got negative 1 in there, which means 1 more electron, right? So everything else going to be the same, and then add 1 electron to the valence shell on the valence level. All right, neon 10, 1s2, 2p2, 2p6. Okay. Magnesium 12, 1s2, 2s2, 2p6. That's 10, 2 more, 3s2. Magnesium 2 plus, right? So it becomes a cation, so loses 2 electrons, right? So we have to get rid 2 electrons of this magnesium. So we go 1s2, 2s2, 2p6, and 3s0, but we don't write it because there's nothing on there. Okay. All right, now condensed electron configuration use a noble gas core. All right. Fluorine, if you look at the periodic table, the noble gas before fluorine is helium. That's a helium core. Yeah, including neon. All is gonna use helium core. So that's helium core, and helium core. Leave out just the valence electron. Okay. For magnesium, it's getting long now. So magnesium is right below neon. That's a new core. Right? So for magnesium, we're going to have magnesium. So neon core and then 3s2. For magnesium 2 plus, it's just like neon. See that? Or it's just neon. That's it. Okay? All right, we're going to close it right here. The octet rule. This is going to help you. We're going to talk about octet rule much more on the next chapter. All right? The octet rule is going to make sense of anything in chemistry. If you don't get octet rule, people have a hard time understanding chemistry because they don't get the octet rule. But the octet rule is super simple. Take a look. An atom is stabilized or stable, becomes stable by having its highest occupied or energy level, which is the valence level, filled. When the valence shell is filled, that's when an atom becomes stable. And most of the I'll explain later. Let's take a look at this first. Okay, the valence shell of helium just 1s, right? 1s, and to fill this 1s up, it's just 2 electrons. So right there. That's why helium is super stable. We call inert gas. Right? It doesn't react with anything. For neon, look at the valence shell. This is the valence shell of neon. The s orbital is full, 2 electrons. The p orbital, 6 electrons, is full as well, right? So all this valence shell is full, 8 electrons total. That's why neon is an inert gas, stable, doesn't do any reaction. Argon, the valence shell of argon is right here. S orbital is full, p orbital is full. Yeah. Krypton, same thing. The valence shell, so for s orbital, this electron is s orbital is full, p orbital is full. That's why helium, neon, argon, krypton, they all are inert gases. Doesn't react with anything, right? So octet rule, why we call it octet? Because most of the time when a valence shell is filled, there are 8 electrons except helium, because helium got only 1 s orbital. If you count the number of valence electrons, 6 plus 2 is 8, 6 plus 2 is 8, 6 plus 2 is 8. So most 99% of atoms elements become stable when the valence shell is filled up to 8 electrons, and they're full. They can't add any more electrons into it. They're super stable. Okay, so except helium, but the rest have 8 electrons when it's becomes stable. So that's we call octet rule. All right. So if you look at right here, so if you use an octet rule, neon, that's 8 valence electrons. See that? So neon is inert gas, so full. Fluorine, the valence shell got 7 electrons total. To become stable like neon, gains 1 more electron. That's the reason why fluorine would love to gain 1 electron, just 1, not 2. Right? Just one, not 2, not 3, just 1 electron. Once they gain 1 electron, it becomes just like neon, stable. That's 8 electrons total. That's octet. The fluoride right here, we call fluoride. The fluoride is octet. That's the reason why fluorine would love to become a fluoride ion and form a compound. Yeah, we learned that in the next chapter. Magnesium on the other hand, so look at the valence shell, 3s2. Oh my God, 2 electrons, 6 electrons to go. Magnesium said, nah, that's too much, 6 electrons, nah. I'm not gonna gain 6 electrons, but I'm gonna lose these 2 electrons. When this magnesium loses 2 electrons, what happened? The valence shell changed from 3s to just 2s and 2p, which already have 8 electrons in it. That's the reason why magnesium would love to become magnesium 2 plus, loses 2 electrons because it becomes stable, just like neon. See that? Right? So magnesium would love to become magnesium ion 2 plus and then form a compound, just like fluorine. Okay? All right. Now, concept test before we go. Potassium metal tend to lose 1 electron, while calcium metal tend to lose 2 electrons. How is it so? Can you explain it? Well, this is what you should do. I'll pause the video and you should do right here. Write the electron configuration of potassium and calcium. Okay? And see why potassium want to lose 1 electron and calcium want to lose 2 electrons. All right, electron configuration, check with me. So calcium, if you look at the periodic table, atomic number is 19, so 19 electrons. So we go 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay, why potassium want to lose 1 electron? Because the inside is already 8. See that? If you lose 1 electron, the valence shell shift from 4s to 3, energy level 3, and that's 8 electrons already. Really stable. Calcium, pretty much the same thing. So calcium look just like potassium, but add 1 more electron. So 4s2 loses 2 electrons, become stable right there. That's a new valence shell. See that? Here we go. Right? That's super simple there. All right, so for the electron configuration, I have a trick for you. Some people like this better than just like 1s2, 2s2, 2p6. It's just memorization. This one is just, you can look at the periodic table. It will tell you what the electron configuration you should do, what in the next orbital you should fill. Look at right here. All right? So, for hydrogen and helium, if you look at the electron configuration of hydrogen and helium, both of them have only s orbital, so 1s1, 1s2. That's just energy level 1. See that? Once the 1s is filled, we have to go up to 2s, like lithium, right? So energy level, the electron configuration of lithium is 1s1, 1s2, 2s1. Go up to energy level 2. This is 2s now. Beryllium, who has 4 electrons, so 1s2, 2s2. Right? Now, once you get to beryllium, 2s is full, we have to go up to 2p orbital. Right? So boron is the first element starting using 2p. 1s2, 2s2, that's 4, and then 1 more, 2p1. So carbon is going to be 2p2, 2p3, 2p4, 2p5, 2p6. Once you get to 2p6, 2p is full. You have to go to the next energy level. Once you go up to the next energy level, which orbital are you using first? S, P, or D? S orbital, sodium right here. So sodium and magnesium will use 3s. That's two electrons in the s orbital. Once you go up to magnesium, the 3s is full. You have to start using 3p orbital. So this guy right here, 6 electron. If you remember, p orbital can fill up to 6 electrons. From aluminum to argon, those are 6 electrons. Right? So 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Once you get to 3p6, you go to 3D. No. You don't go to 3D yet. 3D is locked. Remember, you have to go to 4s first. That's why potassium and calcium use 4s orbital. See that? 4s orbital. Once you get to calcium, 4s is full, you go up to 3D. And if you say, remember, the orbital can fill up to 10 electrons. There are 10 elements right here, up from scandium to zinc, that will fill up 3D orbital. 3D1, 3D2, 3D3, 3D6 for iron, 3D10 of zinc, that's 3D is full. Once 3D is full, you go up to 4P. Gallium is the first one to use 4P. 4P1, 2, 3, 4, 5, 6, and go on from there. For 5S, 4D, 5P, and go on. You get it now. Right? Oh, we have a 4F from here, but we don't talk about that. Okay. Right? So if you use the periodic table, it's much easier, right? So you just go like to the using the periodic table to help you fill up the electrons, do the electron configuration. We have an S block, we have a D block, we have P block, and we have F block right here. But we don't do F block in this course. Okay? All right. Practice one more time. So identify the group element of this characteristic. So this group has a valence electron configuration up to S2, P5. What group is that? If the valence electron, how many valence electron in there? So 7 valence electrons. See that? Group 7. That's it. All group 7 have a 7 valence electron. So, right, all element in group 7 have 7 valence electron. All element in group 1 have 1 valence electron. B, this group of element has a completely filled valence electron. Which group? This is the only group that have completely filled valence electron. That's why they're stable and they don't do a reaction anymore because they're stable. Group 8, filled valence electron. C, this group of element has 1 valence electron. Oh, easy, group 1. So, right. All right, one more, class activity number 4, and the end of chapter 4. I'll see you again on the next chapter.